Hi there, my name is Lane, and today I'm going to be discussing beam magnification and demagnification. This is a technique used to increase or decrease the spot size of a beam and to increase or decrease the power density of the beam. When the beam is magnified, the spot size diameter of the beam increases and the power density decreases. This is expected, as the same number of photons in the beam hits a larger area. Inversely, when the beam is demagnified, the spot size diameter decreases and the power density increases. In this video, I will show an example of a Kepler beam magnification system, which uses two focusing lenses. We will begin with a collimated laser beam, where the light is neither converging nor diverging. Notice how the beam has a consistent diameter for the entire length of the beam. To magnify our beam, I will be using an optical system which contains two lenses of different focal lengths, 200 and 150 millimeters. Before placing the lenses, I cleaned the lenses and checked them for deformities, such as scratches, that may change the shape of the beam. I then estimated approximately where I would place the lens and marked the appropriate places on the table. Our lenses will be separated by the sum of their focal lengths, with the lens of a lower focal length being placed first, in order to magnify our beam. My beam is aligned down the bolt holes of the table, which makes the left and right placement of the lens relatively easy to estimate. Because the beam is collimated, the first lens can be placed anywhere in the beam path with the beam blocked. Each lens has a curved side and a flat side, and the curved side is always placed towards the collimated beam. Now that our first lens has been placed, and I have unblocked the beam, you can see that the beam is no longer collimated. The light is focused down to the focal point of the first lens at 150 millimeters, where it begins expanding again. Notice that the spot size decreases as we approach the focal point before increasing again, larger than it was before a lens was placed. I will now place our second lens, which will collimate the beam again. In order to achieve this, the second lens will be placed with the curved portion of the lens facing out at a distance equal to the sum of the focal lengths of the two lenses. In our case, this is 350 millimeters. As you can see, the beam is now collimated, neither converging nor diverging, past the second lens. Additionally, we have magnified our beam, making the spot size larger and the power density lower than before we inserted our optical system. Inversely, if we wanted to demagnify the beam, I would reverse the system, placing the higher focal length lens first. This would result in a smaller spot size and greater power density. The level of magnification or demagnification can be calculated using the focal lengths of each lens. By dividing the focal length of the second lens in the system by the focal length of the first lens, the level of magnification can be determined. In the case of demagnification, the calculation remains the same, but the lower focal length will be in the numerator, generating a result of 1 over m, or 1 over the level of magnification. An alternative approach to this technique includes using a Galilei beam magnification system, which utilizes a dispersing and collecting lens, rather than two focusing lenses, to prevent overheating within the system at the focal point of the first focusing lens. This is particularly helpful if you are limited in space. Whether you elect to purchase a beam expander or build your own optical system, all beam magnification systems rely on either the Kepler or Galilei principle to modify the spot size and power density of the beam. This technique can be applied in multiple optical systems, including interferometers and remote sensors. Thank you for watching.